Hi everyone, my name is Lokukaluge Perera. I'm an associate professor from the University of Tromso. So the title of this presentation is Advanced Data Analytics Towards Energy Efficient and Emission Reduction, Retrofit Technology Integration in Shipping. So the co-authors of this presentation are Nikolaos Ventikos from National Technical University of Athens, Sven Rolfsen from Utkilen Shipping, and Oster from Wartsila, Finland. So the outline of this presentation is, first I will give you introduction, then the objective of this presentation. So then the main core of this work is the SeaTech project. And part of that project, I'm going to discuss this technology integration framework, which consists of digital models and life cycle cost analysis. So this has been done in a data science environment, and then finally the conclusions will be discussed. So IMO has initiated an extensive greenhouse gas reduction strategy, especially to reduce the carbon intensity in the shipping industry. So this has been done in two levels. The first one is reducing the CO2 emissions per transport work with the target of having considerable reduction, that means at least 40% by 2030 and 70% by 2050 with compared to the 2008 levels. So the second one is the total annual greenhouse gas emission reduction, at least by 50% by 2050 compared to the 2008 levels. So when you compare to these initiatives, two main carbon intensity-based energy efficiency mandatory initiatives being introduced, I would think this consists of two main levels. One is this energy efficiency design index, which is valid for the new ships, and then the energy efficiency existing ship index, which is related to the existing vessels. Since we cannot do any major ship structural modifications for the existing vessels to improve their energy efficiency under the respective operational conditions. So the other possible solution would be to introduce technological innovations as retrofitting technologies, so to satisfy EEXI requirement. However, some of these technologies are in laboratory conditions, but not just the technologies itself, but also the fuel and other energy sources can also be considered as a part of the same process to support the EEXI in ship operational phase. So our research program will contribute to introducing such type of technologies into the market in a data science environment as the main contribution in this project. So the main objective in this study is to quantify energy efficient and emission reduction technology performances in ship by supporting the retrofitting process. As you can imagine, this type of outcome can support the decision-making process of ship owners by having access to the innovation technologies and their performances to achieve the IMO emission reduction targets. So, however, the challenge would be some of these technologies may not be in a realistic operational conditions. Some can be in laboratory conditions or model scale sea trial conditions, but some of these technologies are collecting data. On the other hand, these ocean-going vessels are collecting quite a lot of ship performance and navigation data sets that may not be properly utilized to quantify the performance of these vessels. So the main reason would be the existing mathematical models are inadequate to support these type of data sets to quantify the performances of these vessels. So we are proposing a solution in this project to have a data science environment where two main components will be utilized. One is this advanced data analytics and the second one is the life cycle cost analysis. I will discuss this more detail in my future slides. So let me say a little bit on this SeaTech project. The project title is Next Generation Short Sea Ship, Dual Fuel Engine and Propulsion Retrofit Technologies. The project consists of two innovations. One is the SeaTech engine, which is a combination of diesel and gas engine technologies. And the second one is the dynamic wing or the hydrofoil system, which is mounted in this bow of the vessel. So when you combine these technologies, the project has projected there will be 30% of fuel will be saved under these two technologies, and 46% of the CO2 emission, and then 99% of the SOx and NOx emission, and 94% of the particulate matter emissions will be reduced by these technologies. So the main consortium consists of Wartsila as the project leader, and then Huygens Engineers, a Technical University of Athens, UIT, which is the Arctic University of Norway, which is I am representing, and Leventhal Electronics, and University of Southampton, and Utkilen Shipping. So let's talk about the technology integration framework in this project. So it's mainly divided into three main sections of life cycle cost analysis, then the data handling, mapping and quality assurance section, which is the data pre-processing side, and then performance quantification, which is the data post-processing side. So in the technology wise, we have identified four components. One is the bunker fuel, other one is the SeaTech engine, then the propeller technology, and finally the dynamic wing. So in these technologies, we are looking from materials to the product disposal, because that is the important part of the life cycle cost analysis. In the bunker fuel side, we are looking from the oil and gas fields to the fuel pump cost. And addition to that, engine innovation will be evaluated in a laboratory condition. So there will be data sets from that side also. And then this dynamic wing will be evaluated in large model scale sea trial conditions. So there will be data collected under that process also. So all these data sets we will get fixed into a selected vessel. So this selected vessel will have various technology combinations and operational conditions to do the quantification as the next step. In addition to that, we will consider various wind, wave and current effect with respect to the same vessel. So then the last part of this technology integration framework would be quantification of these technologies. That would be done under this engine propeller combinator diagram. Next slide, I will talk about these digital models. These digital models will be built on top of this engine propeller combinator diagram. So after that, we will introduce various KPIs to quantify these technology performances. There are three main KPI groups will be considered. One is this propulsion power versus engine emission. Other one is the system installation, operational maintenance, disposal, cost versus benefit. And the final one is this environmental impact. One of the basic ideas we came across this study is this digital model. The reason is we looked into the ship performance and navigation data set. Here you are looking into a data set from engine power versus engine speed in your left hand side. So when you looked at this data, we realized this data are clustered. So the reason for these clusters are this vessel is operating, or the engine in this vessel is operating under specific operational modes. So similarly, we looked at other data sets, then we realized even the trim and draft conditions will have different types of operational modes. So that means when you're looking into a ship performance and navigation data sets, you can realize these data are clustered and they have their own orientations. So our interest is to figuring out how these data clusters are distributed, and then what type of a structure having in each of these data clusters. So in the right hand side, this is the mathematical model you would see, which is a representation of this type of a large scale ship performance and navigation data sets. So these clusters can be normal data clusters, so it can be abnormal data clusters. These are often we categorize as a data anomaly clusters. On top of that, there can be outliers throughout this data space. In a majority of situations, these outliers are related to some sort of transition states, or it can be a sensor or DAC fault condition. So that way you can categorize those points also as some type of data anomaly. So let's talk about the life cycle and cost analysis. This has two main components. One is the system life cycle, other one is the fuel life cycle. The environmental profile that we have obtained from the selected vessel will be fed back into this LCC analysis to simulate the performance of these systems for a longer time period. For example, for an engine that can be 20 years. So the main component of the system life cycle would be this product construction tree, where we're looking system from subsystem components towards the material. And then this product construction tree we will utilize throughout the product system life cycle. For example, in the maintenance plan, this product construction tree will be utilized to figure it out the part replacement area. And then the product disposal phase also, we will use the same product construction tree to see what type of materials we will release into the environment. So other than that, when you think about the fuel life cycle, we are doing the cost element from extracting from the oil fields to the delivery into the fuel pump, and then eventually that will be converted into the emissions and the associated cost. So other than that, when we combine these two main components to complete the life cycle cost analysis for this project. So let me explain a little bit on this data science environment also. What we're trying to do here is combining different data sets into a single framework, which is called this hybrid scale study. As you can see in your right hand side, we will consider a case study vessel and we will collect the data sets from that vessel. So we extract the operational profile of that vessel as well as the environmental profile. And these two profiles will be fed back into the model and lab scale study, which is consist of this dynamic wing and then the engine, SeaTech engine. We will initially develop a theoretical engine propeller combinator diagram for this vessel, and the data sets we're collecting from these laboratory conditions and sea trial conditions will integrate into this theoretical engine propeller combinator diagram to see and compare the performances. So these improvements in the performances we will study under this, and then this information we will feed back into this hybrid scale engine propeller combinator diagram, which will be developed from the lessons learned from the theoretical and experimental data as well as the data collected from the full scale vessel. And then life cycle cost analysis section will be integrated into that, eventually to get the KPI calculations to quantify the performance of these technologies. So finally, the conclusion. An overview of integrating energy efficient and emission reduction technologies in a data science environment is discussed, mainly with this SeaTech dual fuel engine and then the biomimetic dynamic wing. So the ultimate objective of this project is to scale up these technologies and demonstrate in a relevant environment with respect to a case study vessel in short sea shipping. So this data science environment consists of two main concepts. One is this advanced data analytics. Eventually we looked into the digital models, but we're heading towards a digital twin concept in the future. And then the life cycle cost analysis to evaluate the technology performance throughout selected innovations. So advanced data analytics and life cycle cost calculations will complement each other, because if there are any uncertainties associated with these technologies, that should also be rectified in this type of study. However, the outcome will eventually open a path towards integrating and evaluating the energy efficient and emission reduction technologies in a data science environment, especially in laboratory conditions. So the ship owners can select appropriate technologies to improve the required energy efficiency gains in their shipping fleets with respect to the innovation technologies. So that is the main contribution of this study. So that is the end of my presentation, and thank you.